Again, I'm Jiyong Park from UNC Greensboro, and I'm happy to talk about the causal inference this week as well. So before we start, do you have any questions regarding the matter we covered last week? So anything about the causal inference? So last week I briefly introduced what the causal inference is and why the causal inference is important, and finally what the potential outcome framework is, which is the most dominant framework for causal inference in social science. So regarding those topics, do you have any questions before we start?
I have a question.
Oh yes, please
okay.
Go ahead.
In terms of research itself, I think research. What is the research different from the practice? Research is finding causal and effects. Yeah. So when I give my lecture to our students, okay, the academic research is the part of the business to find out causes and then the result. So logically, so it's a simple understanding for me. Okay, academic research is a causal and effect, the finding process. So can you say again the causal inference? Briefly, how we can explain to other people causal inference and causal and result?
First of all, I don't think there are differences between research and practice in terms of causal inference, because causal inference is important not only in research but also in practice. For example, currently I'm working with Neighbor, and Neighbor has implemented a platform for A/B test for causal inference, and they try to incorporate the causal inference in their data-driven decision making. Mm-hmm. So in terms of when it comes to the causal inference, the causal inference is important both research and practice. Mm-hmm. And more formally, the causal inference is about the data analytics approach to determine what causes what using data. Yeah, so that's the simple definition of causal inference. And the causal inference itself, the definition of causal inference is very consistent with what we think about the causal effect in daily lives. Mm-hmm. But the key issue is that the data doesn't tell about the causal relationship, because the data does not allow us to distinguish between correlation and causation. So that's mm-hmm. why we need to apply some formal framework, such as potential outcome framework, to mm-hmm. distinguish and separate the causation from correlations in mm-hmm. data. So that's what we do in causal inference. Mm-hmm.
So once again, you're saying is like we have a lot of data, and we can find out data, a volume of data, and the variety of data from the domains. But yeah. Data is just the data. But we cannot exactly match the data how may influence to the next, the dependent variable. So it's a causal inference is try to find out the strong relationship between the independent variable, such as data, and then the result is such as a dependent variable. So the causal inference processing is try to find out the logical, the relationship, causes and result.
Yeah, right. That's right. Mm-hmm. Actually, in academic research, there are many different approaches to establish the causal relationship. For example, one of the most popular approach would be to use theory. So we can use the theory to establish a causal relationship between A and B, mm-hmm. right? Mm-hmm. However, the causal inference I'm talking about last week and this week is a more data-driven approach to establish the causal relationship between A and B. And as you said, so the big data may provide us the more opportunities to find the causal relationship, but big data itself does not guarantee that we can find the causal relationship from them. So the causal inference method enables us to distinguish and separate the correlation from causation. So by doing so, we can establish the more reliable and more credible relationship between the cause and effect based on the data, rather than theory. Yeah, so simply put, you can consider causal inference as a data-driven approach to establish the causal relationship between A and the two variables.
Okay, thank you. Well understood.
Yeah, do you have any other questions? Okay, so if you don't have questions, let me share my screen and let me continue this part. Okay, so first of all, let's quickly recap what I explained last week. So I briefly introduced the potential outcome framework, all right? And under the potential outcome framework, a causal effect is defined as the difference between an actual outcome of the treatment group and its counterfactual if there were no treatment, right? So that's the definition of causal effect according to the potential outcome framework. However, such counterfactual or potential outcome is not observable in reality, right? So our primary goal is to find a comparable control group that shares the similar characteristics to the treatment group, only except whether they get treated or not. So such principle for causal inference is called the ceteris paribus. So I would say that this ceteris paribus is the most important principles for causal inference according to the potential outcome framework. So conceptually, it is straightforward to understand what causal inference is according to the potential outcome framework, right? And then based on these key principles, today I'd like to introduce some popular methods that help us achieve these important principles, ceteris paribus. Okay. And before moving on, let me apologize that I realized I prepared too many slides to cover within this limited time. So today I have to skip some of slides for today, but most slides are self-explanatory, so you can refer to the lecture notes later when you study it in more details. And right, so and if you have any questions, so please feel free to interrupt me and ask, and you can ask in either Korean or English. Okay, so feel free to ask anything. So in English or Korean. So first of all, we need to take a look at the randomized control trials or simply randomized experiments. And I found that subsequent seminars this semester will address a randomized field experiments. So I expect more details about the randomized experiments will be explained there. So today, instead of going into details about the experimental design, how to design experiment and how to conduct experiments, today, let's focus on why and how such randomized experiments can achieve the causal inference according to the potential outcome framework. That's our main focus. So this figure shows a causal hierarchy from the potential outcome perspective. Here, the methodologies at the upper layer generally produce a higher level of causal inference in terms of credibility and the validity. So here you can see that. So you can see that meta-analysis is on the top, right? But this meta-analysis is a research method to systematically synthesize the findings of multiple studies at once. So if a multiple causal inference can be synthesized, then we can have a higher level of confidence in the causal relationship, right? However, so as I said, the meta-analysis is to integrate multiple studies. So as a single method, the most credible method is the randomized control trials, or simply randomized experiments, in which treatment and control groups are assigned through random assignment. Okay, so that's why this randomized control trial is considered the best practice or the gold standard for causal inference. And the important question is, why is this random assignment considered the gold standard of causal inference? So that is our main focus. So once again, I won't explain the details about the experiments because the subsequent seminars will focus more on the field experiments. Okay, so let's focus on why such randomized experiments is the gold standard for causal inference. So let's recall the law of large numbers in statistics, and let's think about the coin flipping. When we flip coins, what is the percentage of heads up or tails up? So easy question, right? It should be 50-50, theoretically. However, as you can see here, the ratio of heads and tails up is not always 50-50, right? Yes. But if we continue to flip the coins, and then it will eventually approach to the 50-50. That's the law of large numbers in statistics. That's exactly the way the random assignment achieved the ceteris paribus. So random assignment is just like the coin flipping. So if we assign a person to the treatment group when the coin heads up, and to the control group when the coin tails up, then we can eventually, evenly distribute any properties to the treatment group and control group, because we can distribute the 50% male to the treatment group and control group, and 50% females to the treatment group and control group, and 50% taller people and 50% smaller people to the treatment and control group, and so forth. So as a result, at least on average, only systematic difference between the two groups will be whether they receive the treatment or not. So for example, let's say there are 100 patients with 50% males and 50% females, and 40% have kids, and their average age is 32, average height is 170 centimeter. And let's say average blood pressure is 100, like this. And then, so if we randomly assign here, so let's randomly assign those 100 patients into two groups, treatment and control groups, right? And then if we randomly assign 50 patients to the treatment group and the other 50 to the control group, then on average, they will be distributed evenly across these two groups, just like the coin flipping, right? So eventually the coin flipping ends up having the 50% of tails up and heads up, right? So based on the law of large numbers, this random assignment allows us to have the similar treatment and control groups, only except they've got treated or not. So simply put, this random assignment is actually the what this random experiments what makes this randomized experiments the gold standard, because this random assignment is the most effective way to achieve the ceteris paribus based on the law of large numbers. So because of the time limit, let me skip this part. So conceptually, it is very straightforward to understand how randomized experiments help us achieve the ceteris paribus. So we can estimate the causal effect of a specific treatment, right? So, however, at the same time, you might think that such experiments are not always feasible in our research, right? Actually, I'm not an experimental researcher. And in my research, I've never conducted randomized controlled trials before. Having said that, the reason why I put emphasis on this RCT, randomized controlled trial for causal inference, is that this RCT should be a reference point for causal inference, even when we use the observational data to estimate the causal effect. So I strongly recommend you think of an ideal RCT, the randomized experiments that you would design if possible, and think how close your empirical strategies using observational data can emulate the hypothetical RCT. That's the basic approach to think about the causal inference method using observational data, because the primary goal of the causal inference method is to emulate RCT, even when such RCT is not feasible. So that's why the RCT is considered the gold standard and reference point for causal inference. So as I emphasized in the beginning, so our primary focus would be to use the observational data for causal inference, because if such randomized experiment is possible, then the best way and the most effective way is to conduct a randomized experiment. But the problem for us is that in many cases, such a randomized experiment is not possible, right? So causal inference are mostly concerned about the causal inference using observational data. So without actual experiments. So the causal inference approach that emulates randomized experiments using observational data is called the quasi-experiment, right? So such quasi-experiments rely on research designs that emulate RCT and random assignments. So that's why this is also called the design-based approach. And as illustrated below, the Nobel Prize in Economics in 2021 recognized the contributions to the design-based approach that aims at emulating a randomized experiment to answer a causal question using observational data. That's our main focus. Okay, so but here, so when it comes to the research design, you don't need to take too seriously, because the research design is not that difficult to understand. So let me take a simple example. So this is a very popular example, and this is one of the Nobel Prize winning research by David Card. I think you have heard of these examples about the natural experiment for the minimum wage. So let's think about this. In order to estimate the causal effect of minimum wage on employment, so what we need to compare. So here, the Card and Kruger focused on the increase in minimum wage in New Jersey. So there was an increase in minimum wage in New Jersey in early 1990s. Okay, so according to the potential outcome framework, these causal effects using this New Jersey data can be theoretically estimated as the difference between employment after the increase in minimum wage in New Jersey and the potential employment if the minimum wage were not increased in New Jersey then, right? That is, according to the potential outcome framework, the causal inference can be estimated by the difference between the actual outcome, actual employment, and potential outcome, potential employment. However, in many cases, such as the minimum wage, it is not easy to conduct the randomized experiments. For example, for example, the treatment group have the higher minimum wage, whereas the control group has the lower minimum wage. So such randomized experiments may raise some social controversies, right? So randomized experiment is not feasible in such case. Therefore, ideally, we could consider a randomized experiment, right? Oh yes, this is the ideal scenario. But so to estimate this ideal scenario, the ideal method is to conduct the randomized experiment. But as I said, this is not easy to conduct in this case. So, but think about the main purpose of these randomized experiments. When we think about the randomized experiment for this case, the main goal is to have the comparable control group. So the comparable control group whose minimum wage remained unchanged, but their characteristics are very similar to the treatment group. That is the main goal of the randomized experiment, right? So even though we cannot conduct an actual experiment, what if we can find a very comparable control group whose minimum wage remained unchanged, but social economic characteristics are very similar to New Jersey? That's the research design adopted in this paper. So here, as you can see in this here, this New Jersey is the kind of the treatment group, right? Because the New Jersey experienced the increase in minimum wage in early 1990s. However, let's focus on this Pennsylvania areas adjacent to New Jersey. So here, the Pennsylvania areas serve as a control group because this area is geographically and economically connected to New Jersey, right? Okay. So this Pennsylvania area, especially adjacent to New Jersey, share many customers and labor market characteristics, right? So customers can visit the restaurant in New Jersey and also visit the restaurants in Pennsylvania. So they share many similar characteristics. However, according to these policies, the restaurant in New Jersey experienced the increase in minimum wage, whereas the restaurant in Pennsylvania did not. So their difference in employment can be attributed to the causal effect of the increase in minimum wage, right? Because on average, the only difference between the restaurant in New Jersey, especially in these adjacent areas, the only difference between the restaurant in New Jersey and restaurant in Pennsylvania is whether their minimum wage increased or not. And most other characteristics are very similar on average. So this is a very typical example of research design. So research design is some situation where we can find a comparable control group that shares the many similarities, only except whether they get treated or not.
Then we can find out the effectiveness of the policy. Minimum wage increase.
Exactly, right.
So last year in the former government in Korea, they increased the minimum wage in Korea, and a lot of the argument and controversial about that increaseness of the minimum wage. How we could measure that minimum wage increase effectiveness how we where do we compare that effect between this similar condition?
Yeah, that's a very good point. Actually, unfortunately, when Korean government increased the minimum wage, it is not easy to find a comparable control group whose minimum wage remains unchanged. Mm-hmm. Unlike this case of New Jersey and Pennsylvania. Okay. But the key principle is to estimate the counterfactors of South Korea. Mm-hmm. Counterfactor of South Korea, if their minimum wage remains unchanged. Mm-hmm. So we can consider several different methods. For example, one of the methods I will introduce later today is the synthetic control. Synthetic control. So here, the Pennsylvania serves as the actual control group, right? But like South Korea, in the case of South Korea, we cannot find actual control group that shares the similarities with the South Korea. Mm-hmm. Right. So in that case, we could constitute a synthetic control by combining the multiple countries. For example, we could combine some trends of the Japan, China, and any other countries. So by combining those other countries, we could reveal some synthetic controls that can serve as a counterfactual for South Korea. So, but even when we constitute a synthetic control, the main principle is exactly the same. Okay. Our goal is to constitute and estimate the counterfactuals for the treatment group, either New Jersey or South Korea.
So it's another question, like the former government, they stressed out the benefit of the minimum age increase, and that it's a huge impact to our economic growth. And then they adopt a case from like a Scandinavia or a Western European countries case. Okay. But the condition is many different from Korean situation. But and the people like a ceteris paribus case, you know, we synthetically control and we try to put our condition into their times when they increase, maybe 1980, 1990, 2000. But, you know, if we can say, okay, but that's the different country and different condition and different times. But how can I compare our South Korean case right now, the 20 years ago in Europe?
Yeah, that's a very good point, because you pointed out the most notable limitation of such causal inference approach. So basically, when we talk about the validity of the research findings, we need to consider the two different types of validity: external validity, and internal validity. Okay. So basically, the most causal inference method aims at maximizing the internal validity. At the same time, the increasing internal validity may sacrifice the external validity. So the external validity is one of the most critical limitations in such a causal inference methods, because such experiment in New Jersey, such a natural experiment in New Jersey may not be applied to other countries like South Korea, and also research findings in the Scandinavian countries may not be applied to South Korea. So such generalizability is about the external validity. So to overcome these limitations of external validities, that's why the meta-analysis has been emphasized in causal inference. Okay. So here. Okay, you can see here, the meta-analysis has been popular to synthesize the multiple causal evidences. So the main purpose of this meta-analysis is to find some contingencies and some conditions where this causal effect is valid and effective or not. So, but still, I don't think the causal evidence in other countries can be directly applied to South Korea because of this limitation.
Okay.
So we need always to keep in mind this limitation of randomized experiments.
Okay, I see.
Yeah, right. So once again, this so the causal inference methodologies try to maximize the internal validity so that the external validity can be sacrificed to a certain extent. So keep in mind that the causal evidence from a single randomized experiment or the natural experiment cannot be generalized to other contexts unless we integrate the multiple evidences at once. Okay, so here, so many basically, let's continue. Let me continue this part. So basically, the quasi-experiment is the design-based approach because the research design, so the quality of causal inference is determined by the research design. Okay, so you will be successful at identifying the causal effect, and not because of the complex statistical models or not because of the big data, but you will be successful because of your effort in developing a research design to emulate the randomized experiments. So the research design is the key point for causal inference according under the potential outcome framework. Okay, so is there any questions so far?
Okay, students, do not hesitate. This is your class. And then speak out whenever you have questions. Okay, let me ask. You know, last 3 years we have COVID-19 all over the world. The COVID-19 affect to all area evenly, equally. So in that case, I want to listen from your opinion. In that case, it's a bit different from the last minimum wage case. It's the same condition we can apply for the different country.
Yeah, you're right. So that's a very good question, because if a treatment is applied exactly the same way across all units, then there is no way to identify the causal effect. However, when we take a closer look at the phenomena, then we can find some variations in some treatment. For example, one recent paper in management science was to take advantage of the shocks in Shincheonji in 2020 in South Korea. So in 2020, even in South Korea, there was geographical variations in the COVID-19 infections, right? Because of the Shincheonji, the Daegu Gyeongbuk area has severely affected by the COVID-19 compared to other areas. So using this natural experiment based on the Shincheonji based the 집단감, the infection, the group infection. So we can compare the outcomes between the Shincheonji, the Daegu Gyeongbuk areas and other areas. So in this way, we should try to find some variations in the treatment of interest.
Okay, right.
Yeah.
That's good. Right.
Hey, thank you for the question. Yeah, that's a very good point. Always, so for research design, we should do our best to find some variations in the treatment so that we can find a comparable control group. So that's a key point. Key point in this approach. And so, likewise, so like the Shincheonji case in terms of the COVID infections. So once we have a research design with comparable control group, the next question is how can we analyze it using data, right? So difference in differences is the most popular models. So the most popular models to analyze such quasi experiments using observational data. So and instead of, so similar to randomized controlled trials, I won't explain the details of this difference in differences models today, but I'd like you to focus on what the difference in differences is and how difference in differences models can achieve the ceteris paribus principle and enable us to estimate the causal effect. So I always think that the conceptual understanding is the most important thing before going into details about the statistical method or some formal model specifications. So the basic idea of DID, difference in differences, is very simple. So first of all, for the DID analysis, we need to observe the outcomes of the treatment and control groups before and after treatment, as you can see here. So for example, so let's think about the Shincheonji examples. And then here, the treatment group can be the Daegu Gyeongbuk area. And comparison groups can be all other areas.
Okay. Rest of our country.
Yes, the rest of our countries. And then the intervention in this case is the 집단 감염 in Shincheonji. So maybe it's around the late February or early March or something. So let's say just March 2020. Okay. And then we can observe the outcomes before and after this Shincheonji 집단 감염 for both groups, Daegu Gyeongbuk group and the rest of countries group. Right, and this is the case when the difference in differences analysis can be applied. Okay, we need to observe those four outcomes like this. And then
how about the counterfactual?
Okay, so let me explain this part. Okay, so here, if we have the four outcomes, then we can calculate the two differences here. The first difference is this. The difference before and after treatment within the treatment group. In this case, the 35 is the difference before and after treatment in the treatment group. And similarly, we can also calculate another difference before and after treatment within the control group, 20. Okay. Right? So we have the two differences, right? And then finally, we can consider one more difference between those two differences. So difference between 35 and 20.
I see.
So that's why this model is called the difference in differences. So we have the two differences, difference in the treatment group and difference in control group. And then the final estimate is the difference in those two differences.
Okay, 15.
Yeah. So if we calculate the difference in differences, then we can get the 15 in these examples. The underlying logic behind this DID is very simple. So once again, record that our goal is to estimate the counterfactual using the control group, right? So the key logic of this DID is that the treatment group would follow the same trend as the control group if there were no treatment. So in the treatment group, so treatment group did not receive the treatment, but over time, their outcome increased by 20, right? So we can reasonably assume that if the treatment group were not treated, then they may follow the similar trends to the control group, like 20. So according to that assumptions, we can assume that each prior outcome 50 plus the time trend in the control group plus 20 can be considered as the counterfactors for the treatment group if they were not treated.
Okay.
So the difference between the treatment group, the actual outcome of the treatment group, and the estimated counterfactor 70 is the causal effect we can obtain from this DID model.
Okay.
So that is the basic, the conceptual idea of the DID.
Okay.
And this is another representation of the DID models. And conceptually, so this DID model is very easy to understand. So, and that's why the DID has been so popular across many disciplines. And it is easy to understand and easy to establish the causal effect and easy to validate the assumption and so forth. So here, however, what is more important is to understand how these DID models enables the causal influence according to the potential outcome framework. And more importantly, to this end, what conditions should be satisfied? So it is, so today, let's focus on the logic of DID for causal inference and what conditions should be met for causal inference. So let's rethink this DID framework from the potential outcome framework and the counterfactual perspective. So here, so let's say the treatment group outcome as T and control group outcome as C. Okay, and here the subscript A and B indicates after and before periods. According to the potential outcome framework, what we need to estimate is the counterfactor of the treatment group, right? So here, so let's say the counterfactor of the treatment group is the T apostrophe A. And then this counterfactor outcome so here, this counterfactor outcome consists of time invariant part and time varying part. So based on this, we can expect that the time invariant outcome is similar to its prior outcome before the treatment because it should be independent of the time.
Okay.
So keeping that in mind, so here the causal effect is basically can be calculated by the difference between the actual outcome in the treatment group and its counterfactor. However, the problem is that we cannot observe this counterfactor. Okay, so let's decompose this counterfactor using the previous outcome TB. And then, so we can rewrite this counterfactor like this. So TB plus T apostrophe A minus TB, right? So by doing so, we can make this TB explicit, right? Here, this TB is observed. So we have data about TB.
Yes.
However, we do not have the data about the T apostrophe A minus TB, right?
Okay.
And it reflects the change in the treatment group over time, the time trends in the treatment group when there were no treatments.
Okay.
So here, we already know this, but we do not have data about this time trend. So what we do is just infer this potential time trend using the control group.
Okay.
So the DID replaces this time trend T apostrophe A minus TB with the time trend in the control group that was not affected by the treatment. So here we can see that the time trend in the control group is the CA minus CB, right? So instead of T apostrophe A minus TB, we can use this CA minus CB.
Okay. Right.
Right then, and then so here this is the estimated counterfactors using the control groups, right?
Okay.
So DID model estimates the counterfactors by combining its the prior outcome TB and time trend in the control group. So this decompositions is very simple, but it allows us to think about what assumptions should be met for the DID analysis.
Okay.
Importantly, the control group doesn't need to be the same as the treatment group in all aspects.
Okay.
Instead, the change over time, that is, the time trend should be comparable between the treatment and control groups.
Okay.
Absent the treatment.
Okay.
This is very strong advantage because so think about this. So for comparisons, let's assume that we don't have observations for the pre-treatment outcomes. In this case, what we can do is just replace this T apostrophe A with the control group outcome CA, right? So if we don't have the pre-treatment outcome, then this TA minus T apostrophe A should be estimated like TA minus CA.
Okay.
In this case, the assumption is that this counterfactor should be comparable to the whole control groups. Okay. So in this case, the assumptions becomes stricter and stronger, right? Okay. However, in this case, in this DID case, we don't need the control group that is similar to to treatment group in all aspects. Okay. Instead, what we need is just a control group that shares the similar time trend to the treatment group. Okay. So what we need is just the similar time trend in control group. Even though the control group have a little different characteristics to the treatment group. So if their time trends are comparable, then this DID allows us to estimate the causal effect.
Sure.
Yeah, that is the key assumption for DID, and this assumption is called
I understand. Okay, let me back to the previous slide. I got a very important question to.
Okay, please go ahead.
The previous slide, the graph. Let me give one example. Yes, this one.
Do you mean this graph? Yeah.
Let me give my example okay. Look, after COVID, a lot of the newspaper said, and expert in tourism, they said travel rebound and travel revenge because of that COVID. Do you understand what I'm saying?
Right.
Okay. Travel rebound or travel revenge is 보복 관광. Anyway, we estimate after COVID, before COVID, okay, that when we are in COVID, like this condition, and then end of endemic, the COVID, we estimate something, the travel revenge to increase something like that. But how we can compare how we can apply that travel revenge if we adopt this DID framework.
Yeah, that depends on what context you are interested in and what context you exploit for your research. Then,
okay. Before COVID, we have a data. We have data. Data is tell us the steady increase from 2015, 2016, 2017, 2018. The inbound the tourist to Korea.
Yeah.
Okay, that's the fact, and we have data. And then the COVID suddenly is a drop down the number.
Yep.
And after COVID, we have to say estimate how inbound travelers will come to Korea. That's gonna be the estimation. And can we apply that the DID framework to that travel revenge with that the previous data like 2014, 15, 16?
Yeah, well, once again, yeah, I think it depends on the context and data characteristics. So for example, I'm not much familiar with the tourism and international travelers context, but if there are some countries that are similar to South Korea in terms of the international tourists, let's assume that there are similar tourism trends in incoming the visiting trends between the Korea and Japan in normal situations and normal conditions, and then we can I don't okay, so I don't know exactly the COVID policies in Japan, but let's say the Japan remains the restriction policies, but the Korea release their restrictions for the foreign travelers, and then in that case we can set the Korea to the treatment group and the Japan as the control group, and then we can compare the incoming trends of foreign travelers, tourists, between the Korea and Japan before and after the policy change, like the policy change in terms of some travel restrictions relief or.
I see. Okay, thank you. It's going to be very important, methodology to measure that kind of a travel revenge after COVID, something like that, comparing Japan and Korea or comparing other countries, similar policy we sustained.
Yeah, right. So, and yeah, but as I said, sometimes. So this difference actually, the next chapter is about the synthetic control, which is very similar to DID, but the synthetic control has a very important advantages over this DID. So, although I take the Japan as an example, but in reality, the Japan may not be directly comparable to the South Korea in terms of the international travelers.
Right.
In that case, so if we cannot find a comparable country in terms of the international travelers, then this DID cannot be applied. Right? In that case, we can average multiple countries at the same time to constitute a synthetic control. So synthetic control is the not real country, but literally the synthetic control group that consists of the multiple countries like Japan, China, US, and India, and any other countries. So if we have the synthetic control, then even when we don't have the comparable control group, we can apply such causal inference method. That's the innovations in synthetic controls. And So let me get back to this point when I talk about the synthetic controls right after this chapter. But what I want to emphasize today is that even when we use different methods, the primary goal is the same.
Mm-hmm.
Most all method is to emulate RCT and to constitute a comparable control group and thereby estimate the counterfactor in reality.
Mm.
The primary goal is exactly the same for all methods: difference in differences, synthetic controls, infinite variables, regression discontinuity. All methods share the goal according to the potential outcome frame.
Mm-hmm.
And once again, here, actually, when you compare these two outcomes in the pre-treatment, pre-intervention, you can see that the outcomes is not the same, right? They are not comparable directly. However, DID allows us to have, so what we need is just a comparable group that shares the similar time trend, right? Mm-hmm. So if their time trends comparable and parallel, then we can use the DID to estimate the counterfactor. So such assumption is called parallel trend assumption.
Okay.
So some assumption that requires for causal inference is generally called the identification assumptions.
Okay.
And identification assumptions for this DID is the parallel trend assumption. So basically the parallel trend assumption, so the parallel trend assumption is not fully verifiable because it is about the time trends between the counterfactor and control group. So after the treatment, we cannot observe the counterfactor, right? However, these parallel trend assumptions requires that the time trends in the counterfactors after treatment should be parallel to the time trend in the control group. Okay. Right? So it cannot be validated using data. However, although we cannot observe the time trends of the counterfactor after the treatment, we can still observe the time trends in both groups before the treatment, okay. Right? Mm-hmm. This is the actual data. Mm-hmm. So what we can show using data is the parallel pretrend. So parallel pretrend is not perfect validation of the parallel trend assumption, but so the parallel pretrend is not sufficient conditions, but necessary conditions. Mm. So in order to make sure this parallel trend assumption is valid, then parallel pretrend must be held. So this parallel pretrend should be validated in your data when you use this DID. So for example, the left figure violates the parallel pretrend. So in this case, the difference in differences cannot be applied. Mm-hmm. But the right figure shows the parallel pretrend, right? So we can apply the DID for the right figure. Okay. So if such pretrends are parallel, then we can reasonably assume that the counterfactor after treatment will follow the parallel time trend with the control group like this. So we can estimate the causal effect by the difference between this actual treatment group and the estimated counterfactors like this. So this is the key identification assumption for DID. So it is critical to validate the parallel pretrend assumptions when you use the DID. Mm-hmm. I see. And it is easy to implement this DID using regressions. So according to the DID framework, the two dummy variables can be defined like this. So here the treatment indicates a dummy variables, the binary variables indicating whether a unit is in the treatment group or not. So if the treatment group, then this binary variable will have value 1, otherwise 0. And this post indicates dummy variables indicating whether the time is after treatment or not, right? And so here, and then we can consider the interactions between the treatment and post. This is the standard regression models for the DID. This is because, so here, let's put the corresponding values of the treatment and post variables for those 4 points. So here, let's think about this first. This is the control group. So the treatment variable will have value 0, so that it will be canceled out. And then this is the pre-intervention. So the post variable will have the value 0, right? So it will also disappear. As a result, only the coefficient remaining is beta 0. Oh, sorry. So this was the treatment group. So this should have the 1 for the treatment, but the post should have the value 0 because it is the pre-treatment. And this will disappear. So beta 0 plus beta 1 will remain for this. Right. Similarly, for this control group, this will also disappear. Right. So this beta 0 will remain for this control group in the pre-treatment. And similarly, so when you think about this control group in the post-treatment, then the treatment will have value 0 because it is the control group, and then the post will have the value 1. Okay. Okay, so this is the 0 and this is 1, and 0 and 1. So it will disappear. So as a result, beta 0 plus beta 2 will remain for this group. And then finally, this treatment group in the post-treatment will have all the value 1 for all variables. As a result, beta 0 plus beta 1 plus beta 2 plus beta 3 will remain. Based on these informations, we can calculate the difference in differences, right? So the first difference before and after treatment in the treatment group is, so the first difference should be beta 2 plus beta 3, right? And then the difference in the control group should be beta 2, right? And then the difference in those differences is so beta 3. So this is the DID estimator. Okay. In this regression model. So in such a standard specification for the DID models, this beta 3 captures the coefficients of our main interest for DID. So this is what I have written just before.
Theoretically, I understand what you explained to me. So the calculation and mathematically it takes time to do calculation, but I think that equation is the 중학교 2학년 수준.
Right. It's the most basic form of the DID models, but there are many advanced forms of the DID, but it is so we don't have much time to explain everything about the advanced DID models. But always the beginning is to learn the most basic and most standard version. So this is the most standard version, standard model for DID.
Anyway, this equation is one kind of the example of the econometrics, isn't it? It's just a starting point.
Yes, it's a part of the econometrics, but econometrics should be more than this simple specifications. And econometrics care about how to estimate the standard errors and how to address the endogeneity and so forth. So, but it should be a part of the econometrics.
Okay. Thank you. Oh, fun.
And so because due to time constraints, let me skip this part for the fixed effects. Okay, then finally, so let me show you an example of these DID models. So this research here, published in Marketing Science, examines the causal effect of the digital distribution of content on physical sales and internet piracy. In doing so, the authors focused on the NBC's decisions to remove its own content from iTunes in 2007 because of a breakdown of the negotiations with Apple. So this exogenous event occurred in late 2007, and all NBC content were affected by this removal. This constitutes the panel data set that can be applied to the DID models, right? So NBC content becomes the treatment group because the NBC contents were removed from the iTunes. And then all other non-NBC contents are included in the control group. Okay. And then there was the treatment in late 2007. So we could observe the outcomes before and after this event. So that's why we can apply the DID models to here. And also you can see that the NBC content and non-NBC content share the parallel time trends. So you can see that the identicance assumption is satisfied here. So this is as I said, this is the standard regression models to analyze such DID models, right? The treatment, after, and then the interaction between treatment and after. And although I won't explain the fixed effects in details, typically in the panel data analysis, the fixed effect should be included. In that case, the main terms of treat and after will be absorbed by the fixed effect. So this treat and after, the main terms are often not shown in the DID regression models because this individual fixed effect will absorb this treatment indicator, and this time fixed effect will absorb this post-treatment indicator. As a result, what remains in the equation is just an interaction term. So you will often see only these interaction terms in the DID models because of this fixed effect. This is the common equation. So for example, in this paper, the following regression models has been used. So here, this T is the time variables, and this NBC is the treatment variable because NBC contents are included in the treatment group. However, you can see that there is no main term for NBC, right? Because of the fixed effect. And also, when the time fixed effects are included, and this T the time indicator will be also dropped. So anyway, the key coefficient for this, key coefficient of our interest, it should be gamma, the interaction term, for the interaction term, NBC multiplied by the DT, the time, the post-treatment time indicator. So this is the typical example of the difference in differences models. There are some more examples, but due to time constraints, let me skip those parts. Because I'd like to, today, I'd like to overview a range of different methods that are so powerful to you, so that you can learn more about this later if you need such a method.
Dr. Park, may I interrupt and Prof?
Yeah, sure, please go ahead.
Oh, if I go to your YouTube, do you have any more explanation about this kind of fixed effects about DID? Do you have a YouTube video about it?
I don't think so. Actually, there are some examples. Examples about the fixed effect already in the lecture notes. So this is the typical data structures for the DID model. So there is the panel unit and time unit, right? So in this simple example, let's consider the effect of mobile push notification on purchase. So here, some customer received the treatment mobile push notification, and some other customers did not receive this notification. So in this example, let's say the customer 1 and 2 received the treatment and received the mobile push notification, and customer 3 did not. It's very clear, right? So this is the treatment group indicator. So customer 1 and 2, the treatment, so customer 1 and 2 will have the value 1 for the treatment group indicator. And let's consider the 3 time period. And then let's say this treatment occurred at time 2. So this post indicator will have value 0 for time 1, day 1. And then day 2 and 3 will have the value 1 for this post indicator, right? And then the interactions can be easily calculated like this.
Okay.
All right. And fixed effect means that fixed effect means the dummy variables for each individuals and each day. For example, there are 3 customers, right? And we want to account for all characteristics of each customer, customer 1, customer 2, and customer 3 individually. And then the easiest way is to consider the indicator for customer 1, indicator for customer 2, and indicator for customer 3. Like this. So this is the customer indicator, customer dummy. So this customer dummy 1 indicates the customer 1. So only customer 1 have the value 1. And the second dummy indicates the customer 2. And the third one indicates the customer 3. So such individual dummies is called the fixed effect. And similarly, we can consider 3 day dummies, right? Day 1 dummy, day 2 dummy, day 3 dummy variables. And this is called the day-time effect or time fixed effect. Right? So by doing so, this customer fixed effect can control for the all time invariant characteristics of each customers. All characteristics for customer 1s, like age or gender or any other characteristics, will be accounted for using this in this dummy. And all characteristics of customer 2 will be explained by this dummy. And all characteristics of customer 3 will be explained by this dummy. This is what the fixed effect play a role in this equation. And this is the same for the time fixed effect. And the thing is that, so let's think about this. Let's consider this. So I've explained that this treatment group will be absorbed by the unit fixed effect. That means that this unit fixed effect, the combination of these three customer dummy variables will perfectly explain this treatment group. For example, let's consider this. So let's say, so for simplicity, let's say CD1, CD2, and CD3. And then this treatment indicator can be predicted perfectly by CD1 plus CD2, right? So because of this, this is the case of the perfect collinearity. So we cannot estimate using regression if the variables are perfectly collinear. So this treatment group is perfectly predicted by the combinations of fixed effect. As a result, when we include this fixed effect, such treatment group cannot be estimated because treatment group is just a part of this fixed effect like this. So that's why this treatment group indicator will be automatically dropped in your regression models. And similarly, when you include this time fixed effect, then this post indicator is perfectly predicted by the combination of time dummy, like post equal day dummy 2 plus day dummy 3, right? As a result, when we include these day dummies, then this post indicator, the post treatment indicator will be automatically dropped because of the perfect collinearity. So that's why in most cases in DID, such main terms of treatment group and post variables will be dropped. So the only interaction terms will remain in the final model specification. So did it answer your question?
Oh yeah, I was just gonna ask you if you have any more detailed explanation in your YouTube. Thank you for the explanation. I appreciate it.
Oh yes, that's a very good point. So let me take another example. So although I won't explain the details about this paper, and what I want to show you is that this is the regression models for DID used in this paper. And you might think that this is different from the regression models for DID we learned in the textbook, because there is only one variables. But still, this regression models is the DID model. Because of the fixed effect, the main terms have been dropped. So that's why only one variable remains in these regression models. And also you can see here, in these examples, only one variable remains in these regressions. But still, this is for the DID models. Because of those fixed effects, the main terms have been dropped. So that's the way the regression models has been used for DID. Okay, is there any other question for DID models?
There's a huge number of questions in my mind, but it's time constraint, and I basically, as long as time allowed, I want to hear from you again in Korean rather than English. It's better for me to understand clearly, okay, later. Yeah, but I want to get this lecture from the scratch, and then next time we will understand better. Okay, keep going on.
Okay, so before moving on to the next method, synthetic controllers, do you have any other question regarding the difference in differences?
Excuse me.
Oh, yeah.
Yeah, if you don't mind, I have a question.
Sure, please go ahead.
So functional relation formulas and graphics are too difficult for me. Causal inference evokes assumptions. Only a few of them can be tested. Any evaluated the extent to which these assumptions can be met so that causal relationships can be inferred to demonstrate the functions of causal thinking and methods. It is said that researchers and in other scientific fields use this approach to explain how knowledge has developed. What are some, is there anything more and so forth? Thank you.
I'm sorry, I didn't get your point. So can you repeat your questions? So what is the key? What was the key point of your question?
Once later, I chose focusing on something later. Thank you.
Okay, sorry.
Okay, we have the 40 minutes to go.
Okay.
And
yeah,
if you have a question, you can send a message to him or through the email.
Yeah, right. So if you cannot ask a question due to the time limit, so feel free to send me an email. So I will be happy to answer any questions. Okay, so let me go very quickly over the synthetic control and the graphical causal model very quickly. So this synthetic control has gained increasing attention recently. Because, for example, this synthetic control method is argued to be the most important innovations in the policy evaluation literature in the last 15 years. So here, the Ethy and Inference are among the top economists in this time. And here's the Inference is one of the Nobel Prize winners in 2021 as well. And that explains how much this synthetic control has received attention from many scholars across disciplines. And this synthetic control is relatively very new. I think it can provide you with great opportunities, especially in the tourism areas. So the applied areas like tourism. So last week I've searched the papers that mention synthetic controls in top tourism journals, but only 2 papers in tourism management and only 1 paper in Journal of Travel Research were found. So that explains the synthetic control can provide a great opportunity for you, and I hope you can fill this gap in this tourism area. Right. So synthetic control is very similar to the difference in differences, but it takes a little different approaches. So the difference in differences, as explained in the previous chapter, the DID basically uses the simple average of outcomes in untreated groups, right, to estimate the treatment group's counterfactors under the parallel trend assumptions. However, synthetic control use the weighted average of outcomes in the control group to estimate the counterfactor. So that is the key difference between difference in differences and the synthetic control. So let me elaborate on this difference between synthetic control and DID with a simple example. So the data structure required for the DID looks like this. So here, as you can see here, let's consider the 5 forms, and let's say the form 1 was treated and the other forms were untreated. So they are control group. And let's say there was a treatment in 2007, and here, using all control units, the difference in differences compares the difference in outcomes between the treated form and average of treated forms. So this DID compares the difference in outcomes between the treated form 1 and average of those untreated forms after treatment with the difference before treatment. So you can simply calculate the DID using this data, right? So here, the outcome for the treatment group in the pre-treatment is 3, and the post-treatment outcome is 4, right? And then we can calculate the average of the control groups before and after treatment. For example, it would be approximately 4.7, and it would be approximately 3.9, right? So difference in differences can be calculated by this. So the first difference is +1. So in the treatment group, so the outcome increased by 1, and then the control group, the outcome decreased by 0.8, right? And then we can calculate the difference in those differences, like +1 minus 0.8. So the DID model will calculate the effect as the 1.8. And this is the result of the difference in differences models. However, as you can see here, the parallel trend assumption is not satisfied, right? Because, so let's compare this. The time trend in the treatment group and the average time trend in the control groups. You can see that the time trend between these two groups are not parallel. That's why DID result is not reliable and not credible. In this case, the first thing you can consider is the matching. So the matching is the statistical tools to constitute the control group that is more comparable to the treatment group. For example, among those 4 forms, on average, in the pre-treatment period, the form 3 is the closest to the treatment group because on average they have the outcome value 3, right? However, still, even when we match the treatment groups to the control groups, sorry, this is not 3. Actually, this is the closest one. So if we apply the matching, then only form 4 will be considered because this control is most comparable to the treatment group. This is the basic idea of matching. However, even though we apply the matching, the parallel trend assumptions cannot be satisfied, right? So out of those 4 forms, there is no comparable control groups that satisfies the parallel trend assumption. So we cannot apply the DID models in this case. However, so the basic idea of synthetic control method is to give some weight to control forms to constitute a synthetic control that resembles the treated forms more closely. So for example, as you can see here, if we consider an average form of form 2 and 3, this synthetic control not only has a parallel pre-trend like this, but also exactly the matches the treated forms outcome before the treatment. So to estimate the causal effect, what we need is the pre-treatment outcomes are exactly the same. So what we need to estimate the causal effect is just to directly compare the outcomes between the treatment form and the synthetic control. Right, so +1 is the result from the synthetic control. This is the basic approach of the synthetic control.
Okay, I see. Interesting.
Yeah, so let me So this is easier examples to compare the differences, compare the DID and synthetic control. So, but keep in mind that the goal of synthetic control and DID is exactly the same. They aim to estimate the counterfactual. Okay, so here, let's consider these data. Y1 indicates the outcomes when a unit received the treatment, and Y0 indicates the potential outcomes when a unit did not receive the treatment. So here, the treatment group, we can observe the actual outcomes before and after treatment like this, right? And then for control group, we can observe the outcomes when they didn't receive the treatment. And this is and according to the potential outcome framework, what we need to estimate is the counterfactual for the treatment group. So this is what we need to estimate for causal inference, even though we cannot directly observe this. And so our goal of DID and synthetic control is to use the control group to estimate this red one counterfactual. That is our main goal. But the DID and synthetic control take a little different approaches to estimate this counterfactual using control groups.
Okay.
So here, the basic idea of DID was to combine the previous outcome of the treatment group with the average time trend of the control group, right? Okay. So under the pair trend assumption, we can reasonably estimate the average treatment effect like this. This was the basic approach, the basic idea of the DID, right? We use the time trends of the control group to estimate the counterfactual. However, the synthetic controls takes a different approach. So first, it trains a prediction models to predict the outcomes of the treatment group in the absence of the treatment group using the control group outcomes. Okay, so for example, so here, using this data in the pre-treatment period, we can predict the treatment group's outcomes like this. So in this case, the first subject's outcome before the treatment can be predicted with the subject 3's outcome, right? And the second subject's outcome before the treatment can be predicted with the subject 4's outcome, right? And then using this, so actually this is a very, very simple examples, but you can apply this concept to the more complex data set as well. And then using these prediction models in the pre-treatment period, we can extrapolate this prediction model to the after period by predicting the counterfactual using the control group's outcomes like this. So this is called the synthetic control. So synthetic control is basically based on the prediction models. So prediction models to predict the treatment group's outcome in the pre-treatment period using the control group's outcome. And then we can estimate the causal effect by directly comparing the outcomes between the treatment group and the synthetic control after treatment. So the good thing is that the parallel trend assumptions is not necessary in this case. So let me take another popular example for the synthetic control. So this research aims to estimate the causal effect of California's anti-tobacco regulations, which was passed and went to effect in 1988. And here, it is clear that the treatment is the enactment of the California's regulations, right? And so here, the outcome of interest is the per capita cigarette sales. So in the US, there are 50 states, right? And California was the only state that introduced such regulation for tobacco at that time. So this treatment group includes only California, and all other 49 states are in the control group.
Okay.
Right? So for causal inference, we can consider the rest of the US and average of all other states as the control groups. However, and basically, we could apply the DID, but as you can see here, this is the average of all other 49 states, and this is the cigarette sales in California treatment group. And you can see that this time trends between the California and the rest of the US are not parallel.
Okay.
Right? So parallel trend assumption is not satisfied. So we cannot apply the DID to this data. And then if we apply the matching techniques, then we should find some comparable state to the California. But as you know, the California is the largest state in the US, so there is no comparable state in the US. Okay. So out of 49 states, there is no comparable state to the California. So it is not easy to apply the matching to this case. Okay. So in this case, the best way is to constitute a synthetic control by combining multiple states. So our goal is to constitute a synthetic California that resembles the cigarette sales in California in the absence of these tobacco regulations. So in this paper, the authors did so by combining some states with different weight. So for example, as you can see here, the Utah and Nevada were given largest weight, followed by Montana, Colorado, and Connecticut. And other states were not considered in creating a synthetic California in terms of the cigarette sales. So you can see here, by combining those states, synthetic control was constituted. And this synthetic California follows exactly the same trend in cigarette sales of California. Right? So by comparing the cigarette sales in actual California and the synthetic California, we can estimate the causal effects of California anti-tobacco regulations on cigarette sales. This is the concept of synthetic control. So the basic idea is not that difficult at all, right? Yeah, but there is some technical details in there because the remaining questions unanswered is how to calculate this weight.
Yes. Yes.
Right.
It's the role of the student.
Yeah, but
not me.
Yeah, think about, so if we can calculate the optimal weight to derive such synthetic California, then we can do causal inference reasonably, right? Okay. And there are many methods, many optimization techniques, and many prediction models to obtain such optimal weights. So you might want to refer to some recent papers about the synthetic control. Okay. But so because of the time limit, so I won't explain the detailed algorithms, but you can easily imagine some predictive models that predict the outcome of California's cigarette sales using the other states, the control groups. So
okay, here's one student raised hand.
Yes.
What's your question?
Please go ahead.
I mean, yeah, just briefly. So do we have to consider about other attributes, something like political preferences or their populations among other states, or should it just care about the dependent variable for here, cigarette sales?
Yeah, that's a very good point. Actually, so when we constitute the synthetic, when we constitute a synthetic control, we can consider not only these the dependent variables outcome, but also some other characteristics. So for example, some socioeconomic characteristics or some political factors, something like that. So it depends on the research context. So if you consider that other characteristics are important to constitute the synthetic control, then the control variables can be considered, can be used to estimate the synthetic
I think
control.
so.
Thank you.
So another student come from Junny, Kim Junny.
Yes, I'm not sure I understand fully about this lecture, but following the question is Professor Gu's question before. Let's say we are studying about the COVID, after COVID tours, something like that, and Professor Bach said we can compare other countries if we cannot find other the reasons in Korea.
Yeah, you're right.
For instance, but in that case, for example, we can find by the numbers the similar countries. We can find the similar countries, for example, Japan and America, to study about the Korean situation. In that case, the America and Japan and Korea are totally different countries. Like for example, the visiting people, the status, all other information can be different, but the numbers can be same. So far, the current numbers can be same. In the case,
it means trend.
Right. Trend can be the same. In the case, if I pick those kind of countries, if I pick those countries, in that case, the result can be very different. In this case, can I say, even though the numbers are same or similar, then can I pick those kind of samples by the numbers?
Yeah, I would say that the synthetic control relies on the data. So focus on what data says about the relationship. So it is basically the data-driven approach for causal inference. So if the data says that they are comparable, then that's it. So for example, let's think about this, the impact of reunification on West Germany. So some argues that the reunification has the negative effect on economies in Germany. But you know, at the time, we are never able to observe the counterfactors on this. And it is not easy to find the comparable countries directly to the West Germany. However, what about this? If we combine the 42% of Austria, 16% of Italy, and 9% of Netherlands, and 11% of Switzerland, and 22% of United States. If we combine those 5 countries with different weight, then the data said that the combination of those 5 countries can predict the economic outcomes in the West Germany. So using those 5 countries, the data-driven approach returned as a result in the synthetic West Germany, so that we can compare the actual GDP of the West Germany and the estimated GDP in the synthetic West Germany. So some people may argue that those 5 countries have different characteristics than West Germany. But so actually nobody knows exactly the truth, but at least the data says that the 5 countries can be used to predict the economic outcomes of the West Germany. So I would say the data. So yeah, so at least if we take the data-driven approach, and I would say the data is the most reliable, credible ones we can rely on.
Thank you very much.
Anyway, it's a very important the information for us. We can use the synthetic control for our study, like combining other countries, comparing to the Germany or California, other states together, whatever. Okay. I think it's essentially for us.
Yeah, this synthetic control has become so popular these days. And there are many extensions after this original synthetic control method. So I recommend
especially, I think, in tourism business, we have a lot of event, convention, exhibition, and the big event, mega event, whatever. So we need to estimate that number of people visiting that event. But how can we measure? Probably we can adopt this as a synthetic control,
exactly right.
Something like that. But in the tourism industry, we don't have real expert who can estimate approximate numbers for potential visitors. This is important.
Yeah, I think the students here are smart enough to learn those methods quickly. And fortunately, there are packages for synthetic controls in R, Stata, and Python as well. So you might want to check out tidy things or things packages in R. This is the most basic model for synthetic control, and this G synthetic is the most advanced one. So this is the original synthetic control method, and recently the more generalized version, which is called the generalized synthetic control, the G things, has been proposed. So you might want to check out those packages. And
I see.
Yeah, that's a key idea of synthetic control. And I have 15 more minutes to go, and so let me very quickly and very briefly explain another approach using causal graph. I think this causal graph is also very useful when you analyze the causal effect using regressions and using the observational data. So this graphical causal models takes a totally different approach from the potential outcome framework. So it is very different from the potential outcome framework because the graphical causal models originate from the computer science and artificial intelligence communities. So let me explain how we can use the causal graph for causal inference. So here, by graph, so I refer to this structure made of nodes and edge, and such causal. So basically, the graphical causal models aims to represent the causal relationships among variables using a data. As a graph, which is called the causal graph, causal diagram, or directed acyclic graph, or simply DAG. So this is the basic approach. So here the nodes represent the variables and the edge represent the causal relationships. So for example, here, these directions indicate the directions of causal relationships. So according to this causal graph, the variable 0 has a causal effect on the variable 1. So it is very intuitive to interpret this causal graph. And there are 4 types of relationship we can identify in here. So for example, here, so let's say the D is the cause and Y is the outcome of interest. And the first one is very straightforward, right? So the direction of edge indicates the causal effect. So this is our interest. And also, so there could be an intermediate variables in the middle of the causal link, right? And it is called the chain structure, and the intermediate variable is called the mediator. And it is for the indirect causal effect. And so the total, so when we want to estimate the total causal effect, then we need to have both direct and indirect causal effect. So it is a very straightforward one. But the most important thing is the next. So we can identify some common causes that affect both cause and effect. Right here, this X has an effect on D and Y at the same time. Right? Such common cause is called confounder, and such a structure is called a fork. And finally, we can consider the common effects that are affected by both cause and effect, right? So here, unlike confounder, this X is affected by not only the cause D, but also the outcome Y, right? Such common effect is called the collider. And this structure with collider is called the immorality. So this is the basic concept about the relationship type in causal graph. And in causal graphs, the associations between different nodes can be analyzed using the information flow. So it is very intuitive to understand, right? So the information of nodes will flow in the direction of edge according to the causal graph. And two different nodes will be associated and correlated if they share the same information. Here, think about the relation between X and Y. And then the information B will flow to A to X. At the same time, the information of B will flow to Z to Y. As a result, X and Y will share the information of B. And there could be many paths that shape the relationship between X and Y. For example, let's think about the C. The information C will flow to Z to X and to D to Y. As a result, X and Y will share the information from C. In this way, the X and Y are correlated to each other. However, here you can, and also there is a direct effect from X, direct information flow from X to Y, right? The X information will flow to W and then flow to Y. And this is the causal effect, indirect causal effect we want to estimate. However, in addition to this indirect causal effect, there are other paths that shape the association between X and Y, like this. This is the non-causal path, and this is another non-causal path, right? So the paths for non-causal associations are called the backdoor paths. Okay, and so understanding this causal graph, it is very straightforward to estimate causal effect. So what should we do to estimate a causal effect when there are not only the causal path, but also non-causal path, backdoor path? So simply put, we should block all backdoor paths. If we can block those backdoor paths, then only causal path will remain so that we can estimate the causal effect. That's the approach of graphical causal models, which is quite different from the potential outcome framework. And okay, so so the key insight of this causal graph is that we can evaluate which variable should be blocked when we estimate the causal effect. So for example, let's consider the three types of structures: the mediator, confounder, and collider. And simply think about the information flow. So here, it is very clear that the information of X will flow to Y through X, right? So the X and Y will be correlated. In this case, it's such relationship is called the D-connected. And similarly, the information of confounder will flow into the X and Y, so that X and Y will share the same information from the confounder. So X and Y will share the same information, so they will be correlated to each other. However, let's think about collider. The information X will flow to Z, but it's not overflow into the Y because there is no direction to them. Similarly, the information of Y go to the Z, but it is not overflow to X. As a result, there is no path that shapes the relationship between X and Y. So this collider doesn't bother us because even in the presence of this collider, X and Y are not correlated to each other because they do not share the information at all. So in that case, it is called de-separated. However, the most important thing is this. So let's consider if we block this mediator, confounder, and collider. So if you are familiar with the regression models, the blocking of variable is equivalent to including a control variable. Okay, so let's say we include the control this M mediator as a control variables and confounder as a control variables and this collider Z as a control variable. Then if we include the variables as control variables, then the information flow through that control variable will be blocked. As a result, the X information cannot be flowed to Y. So after we control for this mediator, X and Y will not be correlated. Similarly, if we control this confounder, then we can hold this confounder fixed. As a result, this information will not flow into the X and Y. So X and Y will not be correlated once we control for this confounder. That is a very straightforward to understand. But the interesting things happen for the collider. At first, when we do not include the collider as control variables, then there was no relation between X and Y. However, if we include the collider as a control variables, then these X information, how I can explain this? Okay, so let me explain here. So when we do not condition control for this collider, the informations will collide each other, not overflow to each other, right? So, but when we condition it, when we control for this collider, then the information of X will bounce toward X, just similar to the act and react law, the 작용 반작용. And similarly, the information of Y will bounce towards Y once this collider is controlled for, blocked. As a result, X and Y will share the common information, so they will be correlated to each other. So simply put, so here the collider is the common results of X and Y, right? So in order to make X and Y return the same results, X and Y should be adjusted in some way that is correlated to each other. So this collider is a very, very important point in graphical models because traditionally people have thought that it is always preferable to include as many control variables as possible. And that's what we have done so far. However, this graphical causal models is warning this practice by showing that such collider variables should not be controlled when we estimate the causal effect, because without these collider variables, there is no correlation between X and Y. However, once we include this collider as control variables, then the correlation between X and Y becomes evident. So the conditioning on colliders can open up a new backdoor path, non-causal path. So it hinders the causal inference. So it is a very important point. So let me very quickly show you these simulation examples to demonstrate the results of controlling for the colliders in regression. So here, let's say XOD is the cause and SBP is the outcome Y. And then here, this H is the confounder, right? And this pro is the collider. Right, and we can consider the different regression models depending on the which variables are included as the control variables. And in this study simulated the data with the true causal effect as 2. So this 2 is the true causal effect true causal effect of SOD on SVP. And then let's consider the 3 different models. The first models do not consider any control variables, and the second one includes only the age confounder. And the third one includes not only the confounder, but also the collider.
Okay. Then
you might think that the third one is better because it includes more control variables than the other ones. However, the regression results seems a little shocking, because so here without control variables, the regression coefficients can be biased, right? Because confounders should be controlled, but failure to control for confounders can also fail to estimate causal effect. And when we control for the confounders, then you can see that regression coefficients is very close to the true effect.
Yes.
However, let's see this. When we include not only the confounder, but also collider, you can see that the regression coefficients are totally messed up. It indicates the opposite effect from the true effect. So it shows that not all control variables are better to be included. Some control variables should not be included, but some control variables should be included. So that's the very important implications of this causal graphs. So there are many guidance paper that explains which variable should be controlled or not in regression context. So I recommend you read some papers you can find in the lecture notes. And this is a good tutorial to explain what is the good controls and what is the bad controls. Yes, and using this control value. So if we have such causal graph, we can estimate the causal effect even using the simple regressions. However, the main issue is that how can you get this causal graph? The first approach is to rely on the literature review. So if we use the literature, previous literature, then we could be able to rebuild such causal graph. And then using this causal graph, we can identify the optimal set of control variables. However, lastly, let me just introduce the name of this approach and bring this approach to your attention. Recently, there has been many advances in this area. So there are many methods that use the data to reveal the causal structure, a causal graph. So such method is called the causal discovery or causal structure discovery. So although there is no time to explain this, I'd like to, I wanted to introduce there is this method, causal discovery, when you are interested in the causal graph.
Okay.
All right, so yeah.
Okay, Professor Park, thank you very much. As time is up, we learn from you new things of us. Okay, here's a lot of stuff to do ahead of us. Okay. I really know about the regression, but it's a totally different world from the original regression. Thank you, Park. Can you say last the comment about anything, toward our students?
Yeah, first of all, it was great. My great pleasure to meet you and deliver a lecture to you about the causal inference. I think the causal inference is a very important research methodology that can be applied to any other research area. So I hope this lecture is helpful for you to adopt a more advanced methodologies in your research. And if you have any questions when you learn about the causal inference after this seminar, so please feel free to email me, and I will be always happy to answer to your emails. And I think so. And thank you for inviting me to these interesting seminars. And I really hope that all students here will take advantage of these opportunities of this seminar presented by other scholars after me. Yeah, thank you very much.
Thank you, Professor Jiyong. When you come to Korea, please knock my door. Or treatment.
Sure,
treatment.
I will do that.
Lobby treatment. Okay. Okay, thank you. Please, big applause to him. Thank you, and I look forward to see you again and face to face. Thank you. Next week we got another seminar, very good seminar. Okay. Look forward to see you next week. Bye.
Yeah, thank you for your attention. Yeah, thank you.
감사합니다.
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 감사합니다.